Hello everyone. I want to talk about enthalpy today. Enthalpy, as you can see here, is the amount of heat energy that's exchanged when a chemical reaction takes place, and these chemical reactions have to be at constant pressure. Okay, so it is heat transfer during a chemical reaction, and again, that has to be under constant pressure. So I did repeat that because those are the three most important parts of enthalpy. Um, and to give you an idea here, enthalpy is heat measured at constant pressure. I should say heat exchanged at constant pressure, and we can measure that heat with a thermometer. So we do see down here that the delta, again, anytime we have a delta or a triangle, that is a delta. Delta enthalpy, or change in enthalpy, is equal to the change in energy, that's internal energy, plus pressure times volume. Pressure times delta V, okay, the change in volume, okay? So when we take a look here at enthalpy, again, just going a little bit further, it is a process, that, again, to repeat, is a process that takes place at constant pressure, and the only work allowed is the volume change. So that's your delta V, and then the internal energy is also delta E. Okay, so this is a little bit how it looks. And you'll notice they use all this stuff. I just wanted to post here. If you really want to look into this, this is how they derive this equation. But really what I want to go down to is that this is the key. Okay, that enthalpy, or delta H, is equal to heat exchanged at constant pressure. So that little p there actually means a whole lot. So heat exchanged at constant pressure. So Q and delta H can mean the same thing as long as you have constant pressure. So it says here at constant pressure only, reading here, the change in enthalpy of a system so the heat lost or gained by the system as a reaction occurs. The change in enthalpy of a system is the heat lost or gained as a chemical reaction occurs. Okay. Um, Now we can calculate work and all that type of stuff, but that only happens when we either produce a gas or use a gas. So just to recap, you can look at this slide a little bit further. But heat given off is negative, heat absorbed is positive, work being done on the surroundings is negative. That means heat is leaving or going out of the system. Excuse me, work is going out of the system. If work is being done on the system, then that's an endothermic or endo work type of thing. And there's the definition of thermodynamics, okay, which is what we're looking at here, okay. Now, I know we looked at this a little bit before, but to go a little bit further, remember, if a reaction produces more gas molecules than reacted, then that's expanding. The system is expanding. Okay, now this something is happening with work. If the system is expanding, that means the system is doing work on the surroundings, or work is leaving to do work on the surroundings. So that's going to be an exothermic or exo type of work, a negative work. If the reaction produces less molecules than the reacted, then the system is going to be compressed. In other words, work is going into the system now from the surroundings, and that's going to be like an endothermic or endo type of work. Okay, no work is done if the gas particles, the gas moles, are equal from beginning to end. Okay, so there are going to be four ways that we look at delta H calculations, and I only put this up here. I don't have to explain them all, but actually the first three here, one, two, three, we're going to be looking at this chapter. And then in the fourth one here, we're going to be looking at not until chapter 7. Okay, we'll do a little bit of that in class. Just going into a little bit of the content-wise here. Um, we will, hold on, I want to get to some more content. Actually, let me do a couple of these. So if we take a look at this particular problem, a gas is compressed against a constant pressure of 3.4 atmospheres, and it's compressed from 27.9 liters to 16.3 liters. During this process, there's a heat gain of the system of 122 joules. Calculate the change in energy of the system, okay? So change in energy of the system, delta E, is equal to Q plus W, okay? So the change in energy of the system is Q plus W. Do we have a heat listed? Uh, let's see here. We have a system. There is a heat gained by the system of 122 joules. So let's go positive 122 joules, okay? But now work, in this case, is work equals negative P delta V. Okay, so let's just expand that out. So I think we're going to have to do a substitution here. Work is negative P delta V. So if I have a negative pressure, oopsie, I didn't mean to write P. Negative. The pressure is 3.4 atmospheres times the delta V, which is always final minus initial. So it's 16.3 minus 27.9. So we want that negative. 16.3 minus 27.9 gives us negative 11.6 liters. So if I multiply negative 11.6 times 3.4 and change the sign, it ends up being 39.4. Okay, so let's see if this makes sense. So we have 39.4. Now again, that's weird because we have liters atmospheres of work, and we'll have to make that conversion here in a second. So is there positive work? Is this thing having work done on it? Is it compressing? Yes, it is. The pressure of 3.4 atmospheres is pushing the system to go from about 28 liters, 27.9, down to 16.3. Okay, so that's a good positive work there. The volume is negative, of course, because we are being compressed. So now that we have liters atmospheres, of course, I have to plug that number in here, but liters atmospheres of work doesn't match joules. So we need to use this conversion right here before we plug into that line. So let me just switch colors here. So we have 39.4 liters atmospheres of work, and I see that the conversion is simply 1 liter atmosphere is equal to 101.3 joules. So I just have to take 39.4 times 101.3. You end up with 3,991 joules. Okay? Just looking here. Okay, so 3,991 joules plus 122 gives us 4,113 joules. 4,113 joules of internal energy in this system. Okay? Let's look at one more. This one is a little bit different, and I want you to see this. So how much heat is released when methane gas is burned? So again, almost an ambiguous question here. But if we take a look at methane gas being burned, it's CH4. That'll react with oxygen because it's being burned, and of course it produces CO2 and H2O. So I think you definitely have to know that going into this, okay? So you need a 2 here and a 2 here, okay? All right, now, it says every time this reaction happens, your delta H, or your enthalpy, releases 890 kilojoules per mole, okay? So every time I burn 1 mole of this, it releases 890 kilojoules. Every time I burn this, it releases 890 kilojoules. Every time you produce this from these, you get 890 kilojoules. Every time you produce this from this, you get 890 kilojoules of energy released. So you see, it does matter that the balanced equation is as specific as it is, because what we're going to do is we're going to take 4.50 grams of methane. And of course, since we're dealing with moles in kilojoules per mole, I got to get that mass into moles. So it's 12 plus 4 is 16 grams of CH4 to 1 mole of CH4. And now that once I have that, I know that CH4, 1 mole of CH4, according to this equation, will burn 890 kilojoules of energy. Okay, so how much heat is released? Of course, that's going to be a negative here. If you left the negative off and added it later, that would be okay too. Okay, or if you just asked the question, how much heat is released, you would say 890 kilojoules of heat is released. Okay, so it doesn't matter how you write that as long as you somehow explain it in the answer. 4.5 divided by 16, press equals, times 890, press equals. You get 250 kilojoules of energy that's released, or I'll say negative 250 kilojoules. If you're talking about a quantity, you could just say 250 kilojoules. But that's how that one works, okay? So again, this is enthalpy. We'll do a ton of these problems, okay? We'll discuss this more in class. I'm just going to look through here to see if there's anything yet. We're getting into a new topic, so I'm going to stop there, okay? If you have any questions, go ahead and email.